So once we've done all of our compaction in the laboratory, we're going to bring our trial mixes back in, and we're going to determine all of our volumetric properties for this mix. And again, your software will do this for you if you're using software, but all of this can be done on a yellow notepad. So we're going to walk through each of these volumetric properties for blend 1. First, we want to determine the VTM, or voids in total mix, where the bulk specific gravity of the mix is 2.394. That's what we got when we bulked our pill. And the maximum specific gravity of the rice is 2.513. You can see the formula here. And we're going to come up with a total VTM of 4.7. So once we've gotten the VTM, we want to determine VMA, or voids in mineral aggregate. Again, our bulk was a 2.394. Our percent stone is 94.5%. Remember, we had 5.5% liquid asphalt. And our bulk specific gravity of the combined aggregate is 2.722. And below is the formula that you'll walk through to get that. And we end up with a 16.9. Next is VFA determination, or voids filled with asphalt. And again, all you need for that calculation is your VTM and your VMA. We got a 16.9 on our VMA and a 4.7. We're going to subtract the 4.7 from the 16.9 and divide that by the VMA of 16.9, and then multiply that by 100, and we're going to end up with 72.2. Percent GMM at N initial, and this is the old tenderness check. This is no longer required by VDOT as a specification, but it's something that we do watch as a tenderness check. To do this calculation, we need the bulk specific gravity of the mix, which is 2.394. We need the rice, which is 2.513. We need the height at N design, which is basically, in this case, if it's a surface mix, it's 50 gyrations. So it's a 114.9. And then we also need a height at N initial, which is 123.9. So here's our calculation, and when you follow these steps, we end up with 88.3. Next thing we want to determine is the effective specific gravity, where our binder is the amount of binder that's not absorbed in the aggregates. And so essentially we're trying to figure out how much of our binder is useful binder. Some of the binder gets absorbed into the aggregate in the process of construction, and we want to know how much binder is actually usable that's taken up space between aggregates. It's given us film thickness. We need to know what the percent binder is, so it's 5.5%. We know that our rice was a 2.513, and we know that the specific gravity of the binder is 1.030. And if you follow the steps below, we get a 2.743 for our effective specific gravity. So using that effective specific gravity, we calculate our effective binder content. So our total binder content is 5.5. The percent stone in the mix is 94.5%. The specific gravity of binder is 1.03. The effective specific gravity of the combined aggregate is 2.743. And the specific gravity of the combined aggregate is 2.722. So again, as I mentioned on the previous slide, we're trying to use our effective specific gravity to calculate what our effective binder content is. And we're going to use this number to determine our fines to asphalt ratio. So if you follow the steps below, you can see that we end up with an effective binder content of 5.21%. Once we've got that effective binder, we can apply that to our percent pass in the 200 sieve, which in this blend was 3.8%. And it's basically just a simple ratio. We take the dust over the asphalt, 3.8 divided by 5.21, and our FA ratio is a 0.7. So here are our volumetric properties that we've calculated for blend 1. We've got 4.7 for our VTM. Remember, our target is 4.0. So we're a little bit loose here. We're going to have to add some asphalt to this mix to get us to the 4.0. VMA is 16.9, VFA 72.2. 88.3 on our N initial, which is less than 89 of the old requirement, so we're in good shape there. And our FA ratio is a 0.7. So if you notice, we've got that same graph pulled down to the right so you can see where we finished. When we're doing volumetric mix design for super pave, we're always trying to get back to 4% air voids, at least for a surface mix. For base mixes, there may be different targets. E-mixes, there may be different targets, so you need to be sure to read your footnotes in section 211. But in this case, we're trying to get to 4% air voids. So we've got to adjust that VTM of 4.7 back to 4%. And we're going to make that adjustment by using asphalt. So one of the first things we have to do is calculate deltas. We need to calculate delta VTM, VMA, and then delta binder. So to calculate delta VTM, we're going to take our 4% air voids and we're going to subtract it. We're going to subtract the actual VTM that we got in our trial blend volumetrics. So we're going to take 4.0 minus 4.7, and that's going to give us a negative 0.7. Delta PB, which is delta binder, is equal to negative 0.4 times delta VTM. So we're going to take negative 0.4 times a negative 0.7. Anytime you have a negative times a negative, that's always going to yield a positive, so we end up with 0.28. And then delta VMA, there are two formulas for delta VMA. You have to select the one that's appropriate for what your air voids did in your trial blend. Our trial blend air voids were 4.7. So if you notice the formulas here, we're going to use the top formula because our air voids were higher, greater than 4.0. So we're going to take 0.2 and multiply that by our delta VTM, which was negative 0.7. A negative times a positive will always yield a negative, so we end up with negative 0.14. So once we have our deltas, now we can estimate what our new asphalt content will be. Once we know what our new asphalt content is, we have to apply that to determine a new estimated VMA and an estimated VFA. Again, we're adjusting our liquid asphalt to get us to 4% air voids, but when we do that, that's going to change the volumetric properties for the rest of the blend. So we have to make the appropriate changes all the way across the board. So our estimated asphalt content, we're going to take the liquid AC that we started with of 5.5, and we're going to add delta PB, which was 0.28, and that gives us a 5.78, which makes sense. We were a little bit loose, so we're going to have to add asphalt to get us to 4%. Our estimated VMA, again, remember that VMA is really not affected by asphalt content. It's mainly affected by gradation. So we're not changing gradation here. One of the things with volumetric mix design, when we're making these adjustments, we're making adjustments in asphalt content only. We're not changing anything with gradation. So we don't anticipate a lot of change here. So the VMA in design was equal to 16.9. We're going to add a negative, and anytime you add a negative means you're basically going to subtract. That drops us to a 16.76 or 16.8. Very little change there. And then estimated VFA, we're going to take our new VMA of 16.8, and one of the keys here, we're going to use our new VTM. And remember, our VTM is always 4.0 when we're doing our deltas, because that's what we're designing to, is 4% air voids. So when we track that 4.0 and divide by the VMA of 16.8, we're going to come up with a 76.2. We also calculated an estimated GMM in initial. So when we do that, we end up with, and we've actually done that prior, but you can use the same calculation, the 88.3 minus a negative 0.7, and we come up with 89%. So after we have done our deltas and adjusted our mix trial blend number 1, To be at 4% air voids with that specific gradation, we're going to have a 5.78 asphalt content. It's going to give us a VMA of 16.8, a VFA of 76.2, and an estimated GMM at initial at 89%. So evaluating compacted trial mixes blend 2. The first thing we want to do is determine our voids and total mix, where our bulk specific gravity of the mix is 2.481 and the maximum theoretical specific gravity of the mix, or the RICE, is 2.541. If you follow through this calculation, you just plug and chug, we're going to get 2.4% VTM, or voids and total mix. Next, we want to determine our VMA. We have to know the bulk specific gravity of the mix, which is 2.481. That's the average of the 3 pills that we did in the lab. Our percent stone of the mix is 94.5%. We just got that by deducting our 5.5% liquid asphalt from 100 to get 94.5. And then we need to know the bulk specific gravity of the combined aggregate, which is 2.769. When we plug those numbers into the formula, we arrive at a 15.3% VMA. VFA, or voids filled with asphalt, is calculated once we know our VMA and our VTM, and essentially it's VMA minus VTM divided by VMA. So we're going to take our 15.3 VMA and subtract the 2.4% air voids divided by 15.3 times 100. Once we go through the calculation, that yields 84.3% VFA, or voids filled with asphalt. Next, we determine our percent GMM at an initial. This is no longer something that is specified by the department. It is something that we still teach just as a tenderness check. To do this, we need to know the bulk specific gravity of the mix, which is a 2.481. We need to know the RICE, or the maximum theoretical specific gravity of the mix, which is a 2.541. The height at in design, which is 50 gyrations, is 114.4. And the height at an initial is 124.1. Once we plug these into the formula, we arrive at a 90.0% GMM at an initial. Next, we need to determine the effective specific gravity, where the percent binder is the amount of binder that's not absorbed in the aggregate. So our percent binder for the mix is 5.5%. Our RICE is 2.541, and the specific gravity of our binder is 1.03. When we go through the calculations and plug into the formula, we come up with a 2.778 effective specific gravity. Once we have an effective specific gravity, we use that to calculate an effective binder content. And essentially, that's the binder content that is not absorbed into the aggregate or the stone. We want to know how much liquid AC is essentially effective. It's got film thickness. It's basically filling the space between the materials and not being absorbed into the stone. So we know that our binder is 5.5%. We know that our percent stone in the mix is 94.5%. The specific gravity of the binder is 1.03. We just calculated the effective specific gravity of the combined aggregate and arrived at a 2.778. And the specific gravity of the combined aggregate is a 2.769. When we plug those into the formula, we arrive at a effective binder content of 5.40%. Once we have an effective binder content, we can calculate our fines to asphalt ratio. Our percent pass in the 200 sieve for this blend is 4.7%. The percent effective binder is 5.4%. We just take those fines of 4.7 and divide by 5.4, and that yields us a 0.9 FA ratio. So blend 2 has yielded us the following volumetric properties. As you can see, our air voids are a little bit low. We're shooting for 4%. We're going to manipulate these and basically adjust our VTM to 4% by changing asphalt content, and that's going to change all of our volumetric properties. So VMA on this trial blend 2 was 15.3, our VFA is 84.3, and our fines to asphalt ratio is a 0.9. So here are our volumetric properties that we calculated in the upper quadrant in our table. Again, we're trying to move that VTM to 4%. We're not going to change gradation to do this, we're going to change asphalt content. We basically want to know with this blend, with this specific gradation, what kind of asphalt content do we need to achieve 4% air voids. So we're going to do that now. We're going to calculate our delta VTM, which the formula for that is 4.0 minus the VTM that we actually achieved in our blend, which was 2.4. So we take 4.0 and subtract 2.4, we get a delta VTM of 1.6. Next, we're going to calculate our delta PB, or our delta binder. That's equal to negative 0.4 times our delta VTM. So delta PB is negative 0.4 times 1.6. A negative times a positive is always a negative, so we yield a negative 0.64 for delta PB. And then finally, we're going to calculate delta VMA. We have to select there are two delta VMA formulas. We're going to select the one that has a VTM of less than 4.0. So we're going to use negative 0.1 times delta VTM, which was 1.6. Because our VTM is less than 4.0. That is going to yield us a negative 0.16. A negative times a positive is always a negative. So once we've got our deltas, we can estimate what our new asphalt content is. When we get a new asphalt content, that is also going to change our volumetric properties for that blend. So our estimated asphalt content, if we take the 5.5 from our trial, and we add a negative 0.64. Anytime that you add a negative as an integer, you're always going to subtract. So that's going to yield us a 4.86 asphalt content for blend 2. And this makes sense. We were at 2.4% air voids. We're going to have to lower asphalt to get to 4%. So it makes sense that we would drop from 5.5 to 4.86. In doing that, that will affect our estimated VMA. We're going to take our trial VMA of 15.3. We're going to add the delta VMA, which is a negative 0.16, and that's going to drop us to 15.14 or 15.1 for VMA. Then once we have our VMA, we can calculate our estimated VFA. Remember that VTM, even though you don't see a new estimated VTM, it is assumed that that's 4.0. All super paved mix design for surface mixes are designed at 4% air void, so our new VTM is 4%. So we're going to take our new estimated VMA of 15.1 and subtract 4.0 and divide by 15.1. That's going to yield us a VFA of design at 73.5. Finally, our GMM at in initial, we finish with a 90.0. We're going to subtract delta VTM, or 1.6, and that's going to give us an 88.4%. So trial blend number 2, we're finishing with a 4.86% binder. Our estimated VTM is 4%. Estimated VMA is 15.1%. Estimated VFA of 73.5%, and an estimated GMM at in initial at 88.4%. So evaluating compacted trial mixes blend 3. The first thing we're going to do is determine our voids and total mix, where our bulk specific gravity of the mix is 2.441. The maximum theoretical specific gravity, or the RICE, of the mix for blend 3 is 2.535. We're going to plug those into the formula, and that's going to yield us a voids and total mix of 3.7%. So next we're going to determine the VMA, or voids and mineral aggregate. To do that, we've got to know the bulk specific gravity of the mix, which is the average of our 3 pills that we tested in the lab, and that yielded a 2.441. Also, we need to know the percent stone, which is just 100% minus our liquid, which is 5.5%. That yields a 94.5%. And we need to know the bulk specific gravity of the combined aggregate, which is a 2.753. When we plug all of those into the formula, we yield a VMA, or voids in mineral aggregate, of 16.2%. Once we have our VTM and VMA, we can determine our VFA, or voids filled with asphalt. The formula for that is just VMA minus VTM divided by VMA times 100%. That's going to yield us a VFA of 77.2%. Lastly, we're going to determine our GMM at N initial. Again, the department does not have a specification for this, but to calculate this formula, we have a bulk specific gravity of the mix we need to know of 2.481. The maximum theoretical specific gravity of the rice is 2.535. The height at N design, which is at 50 gyrations, is 113.0, and the height at N initial is 123.6. If you plug those into the formula, we achieve a GMM, percent GMM at N initial of 88%. And again, this is done as a tenderness check, but is no longer utilized as far as a specification. Next, we want to determine the effective specific gravity, where our binder is the amount of binder that's not absorbed in the asphalt. We need to know this number for a couple of reasons, primarily to figure out what is our percent effective binder that we're going to use in the next formula for our fines to asphalt ratio. To do this, we need the percent binder, which is 5.5%, our maximum theoretical specific gravity of rice of 2.535, and then the specific gravity of binder, which is 1.030. When we plug these into the formula, we end up yielding a 2.771. Once we have our effective specific gravity, we can calculate our effective binder content. Our percent binder, again, is 5.5. Our percent stone in the mix is therefore 94.5%. The specific gravity of binder is 1.03. That will always be given. The effective specific gravity that we just calculated is 2.771, and the specific gravity of the combined aggregate is 2.753. When we plug these into the formula, we yield a 5.31% effective binder content. And remember, effective binder content is the actual effective binder. It's the binder that's giving us film thickness and that's filling up void space between the aggregates that's not absorbed. So once we have that effective binder content, we can calculate a fines to asphalt ratio. Our 200 sieve is 4.5 or 5.4%, and our percent effective binder is 5.31. We're going to take that dust of 5.4, divide it by our effective binder of 5.31, and it yields an FA ratio of 1%. So our blend 3 volumetric properties that we've calculated are a VTM of 3.7, that's pretty close to our design target of 4.0, our VMA of 16.2, VFA of 77.2%. Our percent GMM at an initial at 88%, and then a fines to asphalt ratio of 1.0. So as you can see in the upper right quadrant, we have a table with the volumetric properties that we achieved in blend 3. We're pretty close to the 4.0% air voids that we're shooting for, but we've still got to adjust that total blend of 4% air voids. And to do that, we have to calculate deltas. So first, we're going to calculate delta VTM. We're going to take 4.0, and we're going to subtract the actual VTM that we got in our trial blend of 3.7. So when we subtract 3.7 from 4.0, we yield a 0.3 for our delta VTM. Next, we're going to calculate delta binder, or delta PB. We're going to take a negative 0.4 times delta VTM. So negative 0.4 times 0.3. Anytime we have a negative times a positive, it will always yield a negative, and that yields a negative 0.12. And then lastly, we need to calculate our delta VMA. There are two formulas for that. We're going to select the one that is appropriate for the VTM that we got in our trial blend. So because 3.7 is less than 4.0, we're going to choose the second formula. So we're going to choose negative 0.1 times 0.3, which a negative times a positive is always a negative, and that's going to yield a negative 0.03 for our delta VMA. So our estimated properties of blend 3, once we have got our deltas, we can estimate what is our new asphalt content going to be. Once we've got a new asphalt content, that is in turn going to affect all of our volumetric properties down the line. Again, remember in these blends, we are not adjusting gradation. We're adjusting asphalt content to get to 4% air voids. So in this case, when we adjust our binder, remember we were at 3.7, so we probably don't need to make much of an adjustment to get to 4.0. So our trial blend was 5.5. We're going to add a negative, which was negative 0.12 that we got from delta PB, which drops us to a 5.38. And that makes sense. We were just a little bit on the tight side, not much. We were a 3.7. We're adjusting back to 4.0. So we're saying by our delta calculation that it's going to take 5.38% asphalt to yield 4% air voids for blend 3's gradation. Once we have that, we can calculate our estimated VMA. The VMA of our trial blend was 16.2. We're going to add a negative 0.03. That's going to yield a 16.17, which after we finish the rounding is 16.2. Really no change there. Once we have our new VMA, we can plug that into our estimated VFA calculation. Our new VTM is going to always be 4% at this stage. We're always adjusting back to 4% air voids. So we take 16.2 and subtract 4.0 VTM and divide it by 16.2, which is our new VMA. We yield a 75.3% VFA. So our estimated percent GMM at N initial, we had an 88.0. We're going to subtract our delta VTM of 0.3, and that's going to yield an 87.7%. So below here are our estimated trial blends. And again, we've taken our volumetric properties that we got from our trial blend, actuals, and we've basically just adjusted these by adjusting our liquid asphalt to 4% air voids. So our estimated binder for this specific gradation for blend 3 at 4% air voids will have a 5.38% liquid or binder, a 16.2% VMA, a 75.3% VFA, and an 87.7% GMM at N initial.